These are the notes for LT1 in the energy unit. So the target, the goal here, is to calculate the amount of work done on an object that is moved from one position to another and relate that to the change in energy. So not just understand what work does, but how does that relate to the energy that is used in order to do the work. So there will be a little bit of math here. The formula that you'll be focused on is on the back of your formula sheet, where work is equal to force multiplied by distance, so that's just for reference for later on. Alright, calculating work. So the first thing I want you to do, if we were in class, we would brainstorm the idea of work and energy in physics, because it's not as simple as saying, man, school's a lot of work. Well, what does that mean? Okay, you might do a lot of physics work in weight training. You don't do very much work in terms of the physics definition in physical science, and I know that seems backwards. Energy. What does it mean? Like, it's actually impossible. A lot of us will say, man, I'm out of energy today. No, you're not. Okay, that's not possible. Because if you were out of energy, you would not be able to say that you were out of energy. All right, you wouldn't be able to function. You wouldn't have a heartbeat, anything like that. So we use these terms too loosely, and so now we have to look at more of the science definition of the two. All right, so what we're going to start out with actually is the definition in physics of energy. And energy is the ability to do work. And it's almost like when I give you one definition, there's another vocab word entwined in that. And so what we've got to do also then in the same breath, what is work? Okay, work is applying a force over a distance. We multiply it by that distance. Okay, so you can't have one without the other. It's like two sides of the coin here. So energy allows you to do this. Okay, it allows you to do this work. And when you think about energy, goodness, think about if you ate breakfast today, or if you ate lunch, or if you had a snack, right, something like that. There's so many types of energy. One of them, in food or gasoline in your car, something like that, is chemical potential energy. If you've got that peanut butter and jelly sandwich just sitting there looking at you, it's not doing a darn thing to help you. But as soon as you consume that, your metabolism starts to break it down. All of a sudden, all right, I've got this energy that I can use for something. Well, maybe it allows your heart to contract, muscle contraction. That's kinetic energy. Energy of motion allows you to walk around. Many of us are extremely effective at making sound energy. I'm sure you would say the same of me as I point fingers at some of you. All right, but sound energy, because you got to move those vocal cords. There's the kinetic, and some of that gets turned into sound. Think about thermal energy. Our bodies have to produce thermal energy to stay alive. So there's all kinds of types of energy. And this energy then allows us to do work. Now in the strict physics definition, it's applying a force. Okay, so work depends on two factors. First one is the amount of force applied. So if you pick up a cup of coffee versus you go to try to lift a refrigerator, okay, you think about the difference in the amount of force it would take. All right, so that's what I mean by the amount of force applied. Here's the tricky part. That force must cause the motion of an object. So think about it as in the same direction. Okay, that's the tricky part about this. Okay, the force must cause the motion of an object. It has to be in the same direction. So most of us know what a plank is. Okay, so think about a push-up versus a plank. So we'll usually have our examples on the other side, but oh well. Everybody's had to do a push-up in PE class or in practice or whatever, right? When you push against the ground, you move. Okay, so there's movement in that direction. So that is definitely work. But a plank, if you are unaware of what a plank is, that's where you essentially just hold yourself in the push-up position. It's for core work. And holy moly, if you've planked for 2-3 minutes and your arms are shaking and you're looking like you're shaking like a leaf, and I say, you're not doing any work, you're going to want to get up and kick me. All right, but by a physics definition of it, that is not work, because there is no movement. You're not moving up and down due to the force. So just think about this. If I'm just walking around the room, you guys know I can't draw, so I'm not going to try to draw this, but I'm just holding on to a cup of coffee, just holding on to it, and I'm walking around the room. You might say, well, there's force. Oh, I'll try this, why not? Okay, so here's a person. We'll say it's me, bad hair day, all right? And I've got this cup of coffee. There we go. Think about this. My force that keeps this coffee from falling to the ground is up. So I'm definitely exerting a force on this coffee because gravity's trying to pull it down. Okay, remember this would be an FAP, an applied force. But my motion, if I'm walking around the room, has nothing to do with this. Okay, so I am not doing work on the coffee. Okay, there's no work on that coffee cup. Now you could say I'm doing work on the floor because I'm pushing here and it's causing me to move, so there's that kind of work. But in terms of holding on to the coffee cup, no work at all. Alright, so just think about if somebody's had you hold something really heavy and you're sitting there like holding on to it, waiting, maybe you got to load it into a car or a trailer or something, and it's getting heavy, and by physics definition, it doesn't matter. You are not doing work on it unless you are moving. Alright, so that's a little bit tricky. The last thing to talk about is what is called the work energy theorem. Sounds fancy, it's not too tough. What it says is that the work you do on an object, we could say work causes a change in energy. It's also equal to the change in energy. So in other words, let's say I'm picking something up and sitting on a table. So if we add 20 joules, the unit for work is a joule. We should probably say that. It's a joule. You're also going to see it as a Newton meter because of force is in newtons, and distance is usually based on a meter, multiplied as a Newton meter. These two are interchangeable. So if I add 20 joules of potential energy to a book, so I'm going to take a book and put it up on a shelf. So by lifting it onto a shelf, so if I add 20 joules of potential energy to a book by lifting it onto a shelf, we automatically know that that took 20 joules of work. Those will always be the same. So if I added 20 joules to the book by lifting it up and putting it on the shelf, then that took 20 joules of work. Okay, work causes a change in energy. Work is equal to that amount of energy that is changed. What you'll want to find are LT1 practice problems. Okay, they should be on Moodle, but if not, hopefully you can grab a copy in class, or you can just see these. And remember, our primary formula here, is that work equals force times distance, or the work energy theorem. Okay, those will be our main formulas here. So the first one, number 1, says you carry a 10 Newton bucket. Newtons, force. You're carrying it up 5 meter flights of stairs. Meters, distance. Okay, you are taking the bucket up the stairs. Not so worried about your arms here, but your legs are doing that too. So legs are pushing on the stairs, you are moving up the stairs. So how much work did you do on the bucket? Okay, how much work did you do on the bucket? The bucket is moving with you in the direction of your legs pushing up. So therefore, we say that work is 10 multiplied by 5. So it's 50 Newton meters or 50 joules. Okay, same thing. Okay, 50 Newton meters or 50 joules. Number 2. How much work is required to lift a 150 Newton dumbbell over your head to a height of 2.5 meters? Well, work is force times distance. So we've got our force because we see it in newtons. We have our distance because we see meters. So 150 multiplied by 2.5. 150 times 2.5 gives us 375 Newton meters or 375 joules. Number 6, you're going to exert a 600 Newton force to hold yourself in a push-up position 0.5 meters from the ground. So that's essentially the length of your arms, or maybe you're on your elbows there, your forearms. But you're 0.5 meters from the ground. How much work are you doing? Well, we see a force, we see a distance, and then you need to stop and think. You are holding yourself in a push-up position. There is no motion. So if you're not moving a distance, that's just how far above the ground you are. If you're not moving because of that force, there is no work. So if you saw this on Moodle, the answer would be 0 that you would type in. Okay, no work is being done. 600 newtons multiplied by 0 is still 0. Number 4, there's a horse running down the road, has a kinetic energy of 45,000 joules. How much work must be done to stop the horse? This is not a fancy thing. If a horse is running and it's going to come to a stop, it's going to have to use the road. It's going to do work on the road. It's going to push on that road in order to stop. And we know that work would be equal to this change in energy. In this case, it's a change in kinetic energy. So the work would be whatever number we have on the right-hand side. So 45,000 joules. It would take 45,000 joules of work to bring that 45,000 joules of moving energy to a stop. Number 5, the work done on an object is equal to the amount of energy the object possesses. This is one of the most missed questions on the learning target. It isn't that the work equals the total amount of energy in an object. What we talk about work in terms of is the change in energy. So how much change in energy results in work being done? How much work does it take to change the energy of an object? You have to see the triangle, which means you also would have to see the words change in. Therefore, that is false. It's equal to the amount of energy an object changes, perhaps, if we wanted to reword that. But that one is false because we have to see the change in energy. And that is it for LT1. Good luck.